Hi, welcome to lesson 5 of topic 4. In this lesson, we're going to learn about refraction of light, waves on strings, of sound, and you're going to perform a virtual lab on determining index of refraction experimentally. So, first, a few things to try for yourself at home. All you need is, for this one, any object that can be placed in water. In my case, I used a knife. Some glass, and move the object inside. Level your eyes with the surface of the water and try to observe this. So the second thing I want you to try is put any glass object and pour some water in and move it across and see what happens. And for the third thing, you're going to need a coin to be placed under an empty glass first. Place the glass on top and pour some water over it. Watch the coin from this angle. So let's try to explain what these are all about. The answer is refraction. So first, with this simulation, watch what happens to the wavefronts as they go through a medium, a different medium, and then back into the original medium. You should see that the speed in the original medium is twice the speed they're moving in the middle medium right here, where their wavelength is also half of original. This is what we call refraction. Refraction is the change of speed of a wave due to a change in the medium. Why is light slower in glass? In glass, in water, any transparent medium that is more dense than air, light is slower than it is in air or vacuum. Now, to understand why, we need to think about what kind of wave light is. Remember that light is a transverse wave, but it's also an electromagnetic wave, which means it doesn't need a medium with particles to move or oscillate to transfer the energy. So light travels without the need for a medium, but it can travel inside a medium like air, like glass. So as it passes through a medium, the particles of the medium absorb the energy of the light passing through, which means the denser the medium, the more energy the light is going to lose while traveling in that medium, which is why light is fastest in vacuum, fast in air. We approximate those to be equal actually, so we can say fastest in air and slower in any other transparent medium. So this demonstration is going to show you a top view of a laser light going through a rectangular glass block. Watch what happens to the angle as the light enters and exits the glass block. It's going to enter from the bottom, and this is the normal line because this is the boundary. So this angle is going to be the angle of incidence. As it exits, you're going to look for the point of exit. So the angle between the normal line on the inside of the transparent medium will be the angle made inside the glass block. There we go. See that this is the angle of incidence. That traces what happens underneath the glass block. So I want you to ignore that for a minute. This is where it gets out of the glass block. If you connect that exit point to the entry point, connect that with a line, measure the angle between the normal line and that line, which basically would be this. That is now the angle of refraction, and this is the angle of incidence. In this case, the angle of incidence and angle of refraction are not equal, and they are mathematically related, which we will see in a minute. It's very important that you measure the correct angles. You always have to measure the angle between rays and the normal line, and not the angle between the ray and the medium. Let's see another example, this time a semicircular block. So the ray enters the medium through this boundary, and again, this is the angle of incidence, and you can see the angle of refraction. Well, in this case, the angle of incidence is here, the angle of refraction is there, and you can already see that the change of direction taking place. There's the definition of refraction. It's always correct to make reference to the speed change and not to the direction change, because the direction does not necessarily change in refraction. In the first simulation that we saw, the direction of that wave was not changing, but it was still slowing down, so we still call that refraction. Okay, here's the virtual refraction lab that you will need to do at the end of this lesson. That's the link. So when you go to that page, you're going to see an image like this. This allows us to send an incident ray from here. It will show us the reflected ray as well as the refracted ray. And the vertical line, the normal line, is also given, so you're able to make measurements of angle of incidence, angle of reflection, and angle of refraction. So you see that's the angle of incidence, and that is the angle of refraction, always in the other medium between the ray and the normal line. So these are the measurements you're going to make. As this runs, you can pause and make some measurements. This simulation also allows us to switch the placement of light. So let's see that. This time you can see that the light is going from the dense medium out to the air. And you can see the ray follows the same path back out. So to summarize, we can say that light makes a larger angle with the normal when it is in a free medium than when it is in a more dense medium. Okay, let's explain what we just saw. Snell's Law is the name of the relationship that defines refraction. So let's have a boundary where a light ray goes from air to glass, one transparent medium to another. This is the incident ray, and at the point of incidence, we draw the normal line as our reference. As we defined before, the angle between the incident ray and the normal line is our angle of incidence. Now, in this case, I'm going to extend the normal line to the next medium because this is a transparent medium, and this time, in addition to reflection, there will also be refraction, which means the wave is going to travel into the other medium. But because it's slowing down, instead of going in its original path, which would be this, it's going to now move closer to the normal line. This is now our refracted ray, which means that is our angle of refraction. So, index of refraction is defined as the ratio of speeds. Index of refraction of air is 1 because the reference is always air, so the speed of light in air to the speed of light in air is obviously 1, and this is actually approximated from vacuum. If the medium is more dense, that means light is moving more slowly. So index of refraction is inversely proportional to the speed that the light moves in it. So this ratio has to be equal to speed of light in air divided by the speed of light in the medium. So this is the speed in air, and that is the speed in glass. This relationship applies to wavelength because we define the wave equation as speed equals frequency times the wavelength. Frequency in a transmission like this is not going to change because frequency depends on the source that generates the wave. Once it's out of the source, the frequency cannot change if it is even moving into another medium. So if frequency is constant, you can see from this equation that speed and wavelength are directly proportional, which means I can continue the equation above as such. Since n air is equal to 1, I'm just going to write this as n of glass, C divided by V, and I'm going to put the wavelength in air to the wavelength in glass here. And Snell's law is complete when you relate the angles to this ratio, but not the angles directly, the sine of the angle in air divided by the sine of the angle in the next medium. So that summarizes the Snell's law. Now this is to explain why the angle changes when the wave changes medium. Now I prepared the boundary conditions, including the wavefronts this time. So this is the incident ray, and the red lines are representing the wavefronts. The distance between each wavefront is the wavelength of this ray in air. The wavelengths that reach the boundary first are the ones that will experience the slowdown first. So instead of continuing this way, this point, for example, on this wavefront, cannot travel as it would if it stayed in air, but instead it's in a more dense medium, so it will travel less. So maybe instead of that point, it's going to be over here. So let's get rid of that. Similarly, the other point will be here. Same will happen to this wavefront. Instead of continuing straight, it will have to slow down. Can you see what happened to the distance between the wavefronts? Compare that separation, which would be the wavelength in glass, to that separation, which would be the wavelength of air. You can obviously see that it is smaller. We know that wavefronts are always perpendicular to the rays, which means perpendicular direction to these wavefronts will have to be closer to the normal. This is the summary of what we have just said, and there's the data booklet reference. Let me try to show you the relationship between refraction and wavelength. We're looking at the top view of a setup where I have a ray box, a light box as I used before, white light coming out of it. I have a prism that light will pass through. You can already see the reflection, but you can see that it is moving inside and going out of the other side of the prism. It's obviously changing direction. I want you to focus on what you see on this outgoing ray right here. Keep watching. Do you see the colors already? There it is. So white light is actually a combination of all wavelengths in the visible spectrum. When white light refracts, the wavelengths refract at different angles, which is why we see them separated when light passes through the clouds after a rainbow, because the air is humid, which are water particles in the air, which causes refraction. This concept is called dispersion, and that is how we see a rainbow. And the alignment of colors in the rainbow is not random. So when white light enters the medium, we see that the color that refracts least, meaning the smallest change from its original direction, is red, which has the longest wavelength. Blue, which has the highest frequency or the smallest wavelength, goes through the larger change of direction, so it refracts more than red light. Here I have two pieces of strings attached. A light string, where a pulse is moving fast approaching a boundary between the light spring, and a heavier string, where the pulse is going to slow down. At any boundary between two mediums, three things happen: reflection, refraction, and absorption at the interface, which means the energy splits into three. Some of the wave reflects into its own medium, some of it continues into the second medium, and some energy is lost when this happens. So the wavelength, well, half the wavelength of the incident wave, the size of this pulse is as shown. That reflection is said to act as a fixed end reflection. Remember from the previous lesson what that means. Fixed end reflection means that the wave, when it's reflected, goes through pi phase change. Its wavelength will be the same as incident because it's in the same medium, but it will be inverted, going through a pi phase change. The wavelength of the refracted pulse is smaller than the incident. If a pulse is traveling from a heavy string where it's moving slowly to a lighter string where it's moving fast, that boundary acts as a free end reflection, so the reflected pulse moving back in the same medium has gone through no phase change, which means its wavelength is the same as incident, but the wavelength of the refracted pulse is larger than the incident. Okay, here's another demonstration which I recorded earlier in a previous class, is to show you how sound refracts. So refraction of sound is different from refraction of light. To understand this, you need to think about the nature of those two waves. As I said before, light is an electromagnetic wave, which does not rely on the movement of particles of a medium, but its energy can be absorbed by the particles of the medium as it travels, which means in a denser medium, its energy will be absorbed more by the particles, which means it will be moving more slowly. However, for sound, the conditions are the opposite, because sound relies on the ability of particles delivering the energy from one to another, which means the closer the particles are, the faster the energy is transferred. So the red line of dominoes are stacked more closely, and the blue dominoes are placed more distant from each other. We start the pulse at the same time, and we're going to watch in which line the pulse travels fastest. Let's see. See? What did you see in that? We saw that the red line, where the particles are much closer than the blue, delivered the energy much faster than the blue. And this is how sound works. The closer the particles, the quicker the transmission of energy.
Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream.
Here's another thing I want you to try at home. You're going to see me do it first. I'm warning you, you have to be very gentle while you do this. I want you to put your ear on your table and very, very gently tap on the table. Hear the sound as you observe it coming through the solid because your ear is on the table. Then you put your head up. In the first case, you're going to observe the sound traveling through a solid, and then you're going to observe the sound traveling through air, like that. As you can see, I'm making the same tap, but trust me, I heard different things. Please remember you have to be very gentle when you do this step because otherwise you might hurt your ears and we don't want that. So to summarize refraction of sound in different mediums, we can say when sound goes from dense medium to a less dense medium, unlike light, it slows down. When it goes from a less dense medium to a more dense medium, it actually speeds up. Be very careful about this in exam questions. Alright, that's it from me today. This is your homework. I want you to open this simulation and let it run, and as it runs you can pause anywhere you want. Record 5 pairs of incident and refraction angles. So as the simulation runs, you're going to make measurements of angle of incidence and angle of refractions. Once you have 5 pairs, make another table of sine values of those angles. So you're going to have a table of I versus R first, and then a table of sine I versus sine R. And then looking back at how index of refraction is calculated using Snell's law, figure out a way to plot a suitable graph to determine the refractive index of the glass prism. Once you have the refractive index from your graph, determine the speed of light in the glass prism. Thank you.